Argand diagram. So let's have a look at this complex number that z equals root 3 plus I. And what we want to do here is we're going to create kind of like an xy axis, but it's called an Argand diagram. And instead of an x-axis, we're going to have a real number axis. So these are all the real numbers. And our instead of our y-axis, we're going to have imaginary numbers of z. Now, on our real axis, we have 0 here, 1, 2, 3, even pi, e, negative real numbers, and our imaginary axis consists of all the imaginary numbers. So I, 2i, 3i, minus I, minus 2i, minus 3i. And we can use this Argand diagram to plot complex numbers. And we're going to go ahead and plot that z equals root 3i. So we can see that the real part of z, in this case, equals root 3, and the imaginary part of z equals 1. And this helps us plot this out. So we're going to get root 3 on our real axis and 1 on our y-axis, or I. Sorry, it should be 1. And what we're going to get is a point here, and we can join it to the origin like that. And this represents our complex number z equaling root 3 plus I. Now, we know that this distance is root 3, and we know this distance is 1. But let's just call this distance x and this distance y. Which means that a complex number on the Argand diagram can be represented with z equals x plus iy, which we've already seen before. And we can also just learn some new notation here. So if we know the real part and the imaginary part, we could work out the distance from the origin to that point just using some simple Pythagoras. And that distance we call the modulus. And we give it the symbol with like an absolute value. So we can say the modulus of z is the distance from the origin to that point. And using some simple Pythagoras, that's just going to be the square root of x squared plus y squared. So let's do it for our example. Let's find the modulus of z. That's going to be the square root of root 3 squared plus 1 squared, which is going to give us the square root of root 3 squared is just 3, and 1 squared is 1, and we just get root 4, which equals 2. So now we know the distance from the origin to this point is 2, and that's also the modulus of z. What about the angle from the positive real axis to our complex number? Well, let's analyze this triangle that we now have. So we'd like to find this angle. We know the distance in the y direction is 1, and along the x-axis it's root 3. And this angle from the positive real axis, we actually call the argument of z. So we can write that as arg of z, and this is just going to equal, you can see 1 is just the imaginary part of z, and the root 3 is the real part of z. And we can just use some simple trig and do the inverse tan to find our angle. So we can say it's the inverse tan of 1 over root 3, which is going to give us pi over 6. And just to generalize it, it's going to be the inverse tan of our imaginary part over our real part. Just something we have to note is that the argument of z, we like to define, it has to be between minus pi and pi. And you'll notice it can equal pi, but it can't equal minus pi. This is just our definition, which all that means is the argument exists from here to here, including this angle, and here to here, not including this angle coming this way. Also, if our complex number equals 0, we'll have 0 plus 0i, and the argument of that complex number would be the inverse tan of 0 over 0, and can't divide by 0, so this is undefined. So if you have a complex number that equals 0, the argument is undefined. Now, let's look at expressing our complex number in another form. So we found the modulus and we found the argument. We said we wanted to eat the distance along the x-axis. Let's just call it x again, and let's call this y. And we know this distance is 2, and we know this angle now is equal to pi on 6. So let's write some expressions, some new expressions for x and y. We can say that sine of pi on 6 equals our opposite side, which is y, over our hypotenuse. So y equals 2 times sine pi on 6. We also have cos pi on 6 equals our adjacent side x over our hypotenuse 2. So x equals 2 cos pi on 6. But from our definition of our complex number, we know z equals x plus iy. So we know z is going to equal x, which is 2 cos pi on 6, plus I times 2 sine pi on 6. So we can factorize out at 2 here. So we get 2 outside of cos pi on 6 plus I sine pi on 6. And this is what we call the mod-arg form of the complex number. And just to generalize it a bit more, we can say the mod-arg form of z equals the modulus of z times cos of the argument of z plus I times sine of the argument of z. And the way we usually write this is that we just say z equals, we call the modulus r, and we just say r times cos of some angle theta plus I times sine of that same angle theta. And there's a shortcut to write it. And we say that's r cis theta, where this one should have a bracket around this, and r cis theta, where the c stands for the cos term, the I for the imaginary number I, and the s for the sine term. While we're talking about complex numbers in mod-arg form, let's just have a look at what happens when we multiply two complex numbers in mod-arg form. So if we had z1 equals some modulus r1 multiplied by cos theta 1 plus I sine theta 1, and another complex number z2 equals its own modulus r2 times cos theta 2 plus I sine theta 2. What happens when we multiply these complex numbers together? So we'll have z1 times z2. This is going to equal r1. Let's times the r's together. So we'll have r1 times r2. And then we want to multiply our brackets together. So we'll have cos of theta 1 plus I sine theta 1 times cos theta 2 plus I sine theta 2. Let's go ahead and expand those brackets. So we'll have r1, r2. Expanding these brackets, we're going to get cos theta 1 cos theta 2 plus I. So we're looking at these two terms now. So I times cos theta 1 sine theta 2. Let's go our inside terms. So we've got plus I times cos theta 2 sine theta 1 plus I squared sine theta 1 sine theta 2. See if we can tidy this up a little bit. So we'll have r1, r2. Now, I squared equals minus 1. So then we're going to have, let's think about the real parts first, because these two terms involve imaginary numbers and these two involve just real parts. So we're going to have cos theta 1 cos theta 2 minus sine theta 1 sine theta 2. That all just equals cos of theta 1 plus theta 2 using our compound angle results. Let's factorize out the I out of the next two terms, and we're just left with cos theta 1 sine theta 2 plus cos theta 2 sine theta 1, and that just equals sine of theta 1 plus theta 2 using our compound angle results. And we end up with this expression after we multiply two complex numbers together. And if we just write it in cis form, we're probably able to see what's going on a bit better. So writing it in our cis form, we just get the cis of theta 1 plus theta 2. And you can see by multiplying two complex numbers together, all you need to do is multiply the modulus of them each together and then add the arguments together. So let's do the same thing, but with division. So we're going to use the same complex numbers and divide them. So we're going to go z1 divided by z2. So that's going to give us r1 outside of cos theta 1 plus I sine theta 1 all over R2 times cos theta 2 plus I sine theta 2. Now when we're dividing complex numbers, we multiply by the conjugate of the denominator. So that's exactly what we're going to do. And the conjugate of the denominator is going to be cos theta 2 minus I sine theta 2. And we'll do that same thing in the numerator. Cos theta 2 minus I sine theta 2. And we need to expand this out. So we'll just separate our R1 and R2, and we'll focus on these brackets. So expanding these out, cos theta 1 times cos theta 2 is cos theta 1 cos theta 2. And we're going to get minus I times cos theta 1 sine theta 2 plus I times cos theta 2 sine theta 1 minus I squared sine theta 1 sine theta 2. That's all over cos squared theta 2 minus I times cos theta 2 sine theta 2 plus I cos theta 2 sine theta 2 minus I squared sine squared theta 2. Okay. Minus I squared, well, I squared is minus 1, and minus 1 is going to turn into a plus 1. And same thing down here. So let's see what we're left with. We're left with R1 over R2. Now, looking at the real parts together in the numerator, we're going to have cos theta 1 cos theta 2 plus sine theta 1 sine theta 2. That actually equals cos of theta 1 minus theta 2. Now our next two terms, let's factorize out the I. And let's think about this term being first. So we have cos theta 2 sine theta 1 minus cos theta 1 sine theta 2. That actually equals sine of theta 1 minus theta 2 all over. These two terms cancel out because they're opposites, and we just have cos squared theta 2 plus sine squared theta 2, which is just 1. And then we'll write it in cis form, so we're left with R1 over R2 cis of theta 1 minus theta 2. And what that tells us is that if we're dividing two complex numbers, all we have to do is divide the modulus with each other and subtract the arguments from one another.